scenarios. So you have here you have the real world, and this is the images, that is the rendered image or computer graphics, you can say. And this is sorry, this is the image, and this is the model. So basically, from real world, you so in computer vision, what we do, let's say about the normal vision. So when you are seeing something, let's say you want to detect something, like you want to know whether it's a bird or it's a cat or it's a dog. So that is, you are seeing something and you are perceiving something, that is vision. And in computer graphics, you have some description of the object, or you have some details and you want to render it, or you can say you want to display it in your computer device. That is basically computer graphics. So this is the main loop. Okay. So you can say in computer graphics, you can do modeling, or let's say you want to draw a bird. So how you can draw a bird? You want to start with some minute details. So like you have some smaller elements and you can draw a bird with that. So that is computer graphics. This is that part. And vision is like you want to perceive something from the image. That is vision. So if you follow these rows, you will be able to understand.
Okay.
So from real world, so this is basically saying that from real world, you are taking some image and you're displaying. So when you are displaying it, then it goes back to the real world. So next you can see how this is happening. This can happen. Yeah. So these are basically the display devices. So like when you have the descriptions and you want to display, like this is the TV. That is basically displaying your descriptions, and this is the VR machine, and or the printer. These are basically display devices, and this is like the primary elements. Like this can be either RGB or YMC. YMC means yellow, magenta, and cyan.
Yes.
And this is the history. Do you want to know about this?
No, not important.
And the digital photograph. So when you take a picture, basically you want, so something is out there in the real world and some light is coming from that source, and that light basically needs to be captured. So how we can do it? You can do it using some electronic devices. So that is basically the digital photograph. So cameras, so your smartphone might have some camera, or or you can have your camera, specialized camera devices also for that. This is the image sensors. So basically what it says is that there are two types of sensors. It can be either CCD sensor or the CMOS sensor. That is, some light is coming from the source, and that light is converted into pixels. Right. So pixel is basically the camera's way of taking the real world scenario. So once it is converted into pixels, it can do computer vision tasks, or like you can say computer graphics also from that. This is the church couple display or CCD device. So that is basically, so first let's go into this scenario analogy. So what here happening is, so some rain, so you can visualize it, right? So some raindrops are falling and some bucket is collecting that water, and that whole water is collected into this serial bucket array, and then finally it is collected. So this is this can the CCD devices working principle is similar to that. So incoming photos are coming, and that is stored in some potential world, and then finally it is getting rendered in this voltage display.
Okay.
Okay, now this is the CMOS. This is also similar. So it is basically taking the photons, or the light what's coming, and that is getting converted into pixel. You don't need the explanation of this, right?
No, it's fine.
Yeah. This is a pair pattern. So what happens in pair pattern is that you can estimate each pixels using RGB. Right?
Mm.
So basically, with different ratios of red, green, and blue, you can render any pixel.
Mm.
So like, so and the human perception is like it can see green. I mean, the green wavelength is much more sensitive to our eyes.
Yes.
So that is, I mean, you can see more number of greens here. That's right,
Mm. Mm-hmm.
and the red and blues are, I mean, less.
Yes.
It's a scanner. So scanner is also similar. It is, I mean, it is seeing some object and some light is falling into that, and that is basically giving you some digital protocol.
Okay. Yeah.
And one more thing, so your coding will be in Python or MATLAB?
Python. In Python.
So this is stereo vision. So stereo vision is something what you can say you want to estimate some depth of some object. So how we can estimate the depth of let's say if you see something in front of like a bottle, how you estimate the depth of a bottle? You basically take two copies of that photo using your both left and right eyes, and you estimate depth from that. That is the stereo estimation. I mean, this depth estimation using stereo vision. So that is
Okay.
how humans do it. But in case of machines, this is the depth estimation machine. So what it is doing is it is sending some pulsed code to the object, and using the reflected code, it is able to estimate the depth of that object. How far is it?
Mm.
And even using two images, you can also estimate a depth of any object if you have two or three images. So that will be basically a multivision or stereo vision depth estimation.
Mm.
This is how it is doing it. This is the estimated depth, and this is the color coded video.
Okay.
This is also another device. LIDAR. So far we have seen the devices which are acquiring the images, right?
Yes.
Sorry,
Yes.
acquiring some knowledge
No. Yes.
given from the real world scenario.
Mm.
So that is basically the acquisition part, and this is the
Mm.
display. How you're able to display an image.
Mm.
So you can do it either using a TV or so for in case of a mobile, the display along with the sensor, both of them are in the display device. So you are
Mm.
able to see something on your mobile and also operate on that. So basically there is also a sensor in that, but in case of
Okay.
TV, there is no sensor. It is only display. So
Yes.
there is no computation in that. It is just some sort of LCD or LED in that.
Mm-hmm.
This is the LCD device. So LCD, I think you don't need much explanation of these things, right?
It's fine. Yeah.
Basically the hardware and how the device is able to
It works.
display the images or
Yeah.
LCD. And this is a virtual reality device. This is using the DMDRM. This is very important in case of this virtual reality device. Even in case of medical imaging, this DMDRM is widely used.
Mm-hmm.
Yeah. So do you want the explanation of all these things?
No, it's fine.
Yeah. So let me see. So do you want the explanation of all these things? I mean, these are nothing related to coding. Or should I
This is
directly?
mainly, yeah, the general idea. So it's
Uh,
fine.
so should I directly go into the digital image processing part?
Yeah.
So this is the pair pattern. So which I have just explained.
Yes.
This is basically a filter of R, G, and B's.
Hmm.
And this was a stereo vision. So the basic computation starts from here. So the quantization.
Hmm.
So so in an image is basically comprised of pixels, and those
Hmm.
pixels, I mean, how are they stored in the memory? So that is basically quantization. You cannot continuously store a full colored image in memory, right? You just store information of small pixels. I mean, how long is the pixel and all those
Hmm.
information in your memory,
Hmm.
and that also needs to be quantized or converted
Okay.
into bytes, bits and bytes
Oh,
to store in the memory.
okay.
This is example. So you can see this is the one bit examples, that is you have only white or black. Then the
Yes.
pixel does not contain much information. As you
Hmm.
increase the number of bits or number of labels, the image is getting much more clear. So
Hmm.
if you have 8 bits of for each pixel,
Hmm.
that is a grayscale level, the picture is much more clear.
Okay.
And the memory is also getting increased. So so to store this image, we don't need much memory, as we
Yes.
have less number of bits. But for this image, we need bigger memory.
Yeah.
So error diffusion achieves visually more pleasing results by distributing quantization errors across memory pixels. Uh, so so you want to acquire some knowledge from the image. So what
Hmm.
you can do is you can give a threshold, right? So depending on the threshold, this
Hmm.
image will be converted into so like basically like so this part. So if you want to convert this image into that image, how you can do that? You can basically take each pixel information, then you can do a
Hmm.
hard thresholding. If the pixel intensity is below that threshold, then it will be converted into black. And if that intensity is more than that threshold, then it will be converted to white. So that's how you can convert this into this. That is
Okay.
the hard thresholding. And
Mm-hmm.
this error diffusion is basically the difference of this this one and that
Okay.
one. This is the pseudopolar fan. So this is you are able to see that. See, right?
Yes.
So this is for the y-x part. The loop. So if the intensity is below 128, then it is
Mm-hmm.
converted to 0.
Yes.
And the error is basically the input image minus the 0, that is output image, the difference of these two. And if
Mm-hmm.
the intensity is 255, then only it is the error is input image minus x. Sorry,
Mm-hmm.
output image is directly converted to
Mm-hmm.
55. That is,
Zero.
if the intensity is more than 128, then it is converted to 255. That is the white scale.
Yes.
And if the intensity is less than 128, then it is turned to 0 or the black.
Mm-hmm.
And the error is basically the image minus 255. Image intensity minus 255.
Okay.
And, So error to right. So the error is basically passed to right side and left side. So there, this part is good.
Yes.
So this is the histogram. Histogram is basically, I mean, the plot of the intensity. So what it is doing is, so if you take let's say you're taking a grayscale image. So you can remember, right? For grayscale image, the pixels intensities are like with 3 bits or 4 bit or 8 bits. So you can
Yes.
basically plot that. So this plot is giving the intensity histogram. So this part has a higher intensity. That's why it's on the higher side.
Okay.
This part have so this is the medium intensity part that is rendered here, and this is the lower part, so that is close to zero.
Yeah.
The number of this low intensity images is high.
Yes.
That's why here this graph is on the higher side, and this intensity is on the medium range, around 128. And this part is having the higher, I mean, the highest intensity, that is the white part. This part is having the number that is medium. Similarly, you can also plot Rgb histogram. That is the red, I mean, how much intense red portion is there on this image. That is the red histogram. This is the blue histogram. Sorry, this is the red histogram, and this is the blue histogram. Or you can also see the grade level histograms.
Yes. Yeah.
This is the per pixel processing, or you can do some inversion. So, so this is basically what it is doing. This is subtracting the pixel intensity from 255. So that is this is inverted, right? So this is like the 255 minus the highest portion will be the least portion.
Yes.
It's like that. No, no. 255 the image intensity.
Yes.
So like that is the inversion process, right? You're able to the highest portion here, it is converted to this part.
Yes.
And basically it is inverted with respect to the y-axis. It's the contrast enhancement. So like I mean like
Color.
saying something.
Like increasing the color contrast.
The contrast of that image.
Yeah.
The most important operation for image processing. All the recent technologies done using this convolution. Convolution is like let's take this portion for the image. So this portion is basically, I mean, this is the, let's say this is the filter. I mean, for convolution you need two parts. One is this is basically this is the kernel. This part is the kernel, and this is the image. The image is convolved with the kernel, and that is basically giving you some features or descriptors. And that mathematical operation is here. So the convolution operation can take like so you basically overlap this kernel onto that portion, this center pixel, and you multiply all the corresponding pixel locations and get the sum of it. So if you see from this block, this is basically -4 into 2. That's why it is -8.
Yes. Yeah.
All other portion is 0. Here, all of the portions are 0, and this part is 4. That's multiplied with 0. That's why all other portions are 0. So only this 2 and this -4 are multiplied. That's why it is -8.
Yeah.
So that's how this kernel is basically shifted from left to right with some stride. The stride is also optional. You can shift this filter by one position or two position. Depending on that, you get some output feature descriptor.
Okay. Yes.
And this is the most important thing of current image processing technology, because this convolution part, what it is giving is the features or the descriptors of this image, and which can be used for getting the knowledge of the image. And this filter is basically changed differently. So you can have different types of filters, like you can have bin filters, you can have difference filter, or you can have averaging filter or median filter. Depending on that, you will acquire some knowledge of this image. That part. So this is also a visualized, some convolution visualized. You can see from this demo. So what this is basically doing is, I explained you, right? You understood what I said.
Yes, yes.
So as I've said, so depending on the kernels, you can have different types of operations on the image. So if you want to, so let's say you want to compress the image into a less number of bits or less number of pixels. So what you can do is, like, you can do some averaging operation, and you can just store that small number of pixels into your memory. So that will basically reduce the size of your memory using this averaging, this box filter or the average filter. It will just reduce the image size. You can do that.
Okay.
Or you can also do, this is basically the blurring operation. Okay? So you might take a photo from a high resolution camera, and you don't have that much memory to store it in your device. So that then what you can do is, you can just blur that photo and then store it in the memory. That is the blurring device. Or you can say this is also low pass filter. So that is basically removing your high frequency components or the details of the image. So details means, if the difference between neighboring pixels will have some information, and the statistics of different neighborhood have different relations. Then those parts will be removed using this low pass filter or the averaging filter.
Okay. Yes.
So this is the gradient filter. So in case of, so basically there are two types of gradient filters. One is the horizontal gradient and one is the vertical gradient. So in case of horizontal gradients, you can see the columns of this kernel matrix is just the invert of these two. So in case of horizontal gradient,
Yes.
but in this case the columns are the different two opposite. In case of vertical gradients, where you are just taking the vertical differences, then the rows are negative on each other. And in case of diagonal, you can have like this. This is the -1, this -1, and 1 is 1.
Yes.
This will acquire the diagonal elements, the diagonal details, the difference of. All these three filters are known as Sobel filter. You can have some other filters also, depending on your difference operation. You can have some other filters as well. This is the motion blur. That's also important, interesting. So if you take a photo with some motion in your camera, there will be some error. So that will be basically, your neighborhood pixels are getting overlapped, right? So you don't have much details information in that motion blur picture. If you want to remove that motion blur, you can do this unsharp masking operation. This operation will bring out the details of that motion blur. So this is basically the inverse of the blurring operation.
Okay.
This is CNN. Whatever that the convolution is doing. So you can see. So this is the input image, and you have using the first convolution operation, you get the feature map.
Yes.
and the size of the feature map will depend on the convolutional kernels. Again, you can do some subsampling. Then that feature map size will get reduced. Then again, so this is basically the operation that is for used in CNN. This is, I mean,
Okay.
CNN is very important for this image processing and machine learning. So this CNN is like giving you the details of this image, and that is basically fed into some neural network.
Okay.
CNN part. So this is basically taking. So let's say this feature map can be the that difference filter, or it can be blurring filter, or it can be horizontal difference filter. It can be anything. And that those feature maps are then subsampled, and there is also something called stride. That striding subsampling, it can do some downsampling. It can also do upsampling. All these operations can happen in between. And that is then finally that is flattened. Like you have this is like the, I mean, this row of matrices are then flattened, and that is giving you the output. That this is basically the description of this image, and that is fed to some neural networks to get some to acquire some knowledge about that image.
Okay.
Some median filtering. So median filtering, basically you are taking the median of the image of a particular portion. So, so my implementation will do like sort all the pixel values, and it will take the middle value. So so if you take some let's say this portion, what you will do is you will just flatten it out using some histogram operation, and the middlemost value will be given in the output type value. So if you can have 1 pixel median filter, or 3px or 10px. So as the size of that median filter is increased, the details of this image is
Got it. Yes.
This is the median example of a median filter. So this median filter is used to remove this salt and pepper noise. So this is the input image. You have this salt and pepper noise. You will remove that you can do using this median filtered output.
Okay.
And this is the morphological operation. So morphological operation is like it can. So there are basically two morphological operation. One is the erosion, and other one is the dilation.
Okay.
This is the input image, and so an opening operation is basically erosion followed by dilation. Closing operation is opposite. Using these two operations, you can do either opening or closing.
Yes.
So that is basically, I mean, this image is the white portion is getting thin, and in this case, the right portion, the white portion is getting better. I mean, it is getting much more. The depth is getting. So do you want to? So do you have any questions?
As of now, no. Yeah.
And what? So you can talk to the.
Who should I talk to?
Can you stop